Thank you. So what I'd like to do now is start with this demo. And so this is called Quakecaster, and it'll introduce you to everything you need to know to understand the talk, which is how these Turkish earthquakes are interacting. Now, this is the earthquake machine, and there are 4 elements in it. And I submit that if you have all of these 4 elements, you always and only get earthquakes. And if you're missing any one of them, you never get earthquakes. So what are they? First, there's the steady motion of the plate's interiors, which I'm going to represent by cranking on this casting reel. And that's attached to a rubber band. And that rubber band represents the rubberiness, the elasticity of the Earth's crust. And that rubber band is connected to kitchen countertop samples, which are the mass that's going to move in an earthquake. And they're sitting on top of an industrial non-skid surface. Okay, so those are the 4 elements. And now what I'm going to do is I'm going to crank steadily, and I want you to watch what's happening in the experiment. Okay, so we waited every couple hundred or so years, and then we had an earthquake, right? So let me ask you some questions. Are all the earthquakes the same size if I measure size by how much they moved? No. Were all the earthquakes separated by the same amount of time? No. If this is very bad news, if I can't make regular repeating earthquakes with Home Depot sandpaper, kitchen countertop samples, and a rubber band, I'm never going to get them in the earth, because the mass that moves in earthquakes is more variable. The elasticity of the earth varies also. We have granite, we have basalt, we have sediments. They don't all have the same elastic properties. This non-skid surface is very, very uniform. If I feel it on it feels uniformly rough. But the roughness of faults has got to be much more variable, because we have bends and breaks in fault zones. And some faults have gouge in them, a kind of ground down powder, and some don't. So this variability is the bitter pill that seismologists have had to swallow in 40 years of fruitless exercise to try to learn how to predict earthquakes. That variability is real, and it's something that we have to accept. And anybody who says, oh, I know what the largest earthquake can be on the East Anatolian Fault, or the San Andreas, or the New Madrid Fault, is kidding themselves, because there's an enormous amount of variability in this system. Okay, now let's do something. This has been a 2-bricker. What if I take 1 brick off, and now I have a 1-bricker? Okay, so let's think about it. I'm going to crank at the same speed. It's the same rubber band. Everything is the same except the weight, the mass resisting motion. So what am I going to get? If I crank at the same speed as before, am I going to get fewer earthquakes or more? Are they going to be larger or smaller? So in your mind, ask yourself what that's going to be. And now let's watch. So they are about half the size, right? If we measure size by how much they slip, and about twice the frequency. And that makes sense from the standpoint that the force resisting motion is the weight of the brick times the friction, about 1/2. And the force pulling on it is the length change of the spring times its stiffness. So if I have the resistance, I'm going to go more frequently, but the spring isn't going to be as stretched out as it was before. So it's going to go a shorter distance. And we have places on the San Andreas, we have the Parkfield section, which rather than producing 8s, like the northernmost and southernmost part of the fault, it's producing 6s much more frequently, every 20 to 30 years, rather than every 200 to 400 years for the big quakes. So we can get an enormous amount of variability in the size of earthquakes with everything else being the same. And now let me take it 1 step further. What we've done here is we've sandblasted the bottom of this kitchen countertop sample. So it's rough, more or less like what we would expect in a fault zone. But the other side was supposed to be on the countertop. So you can see it catches the light, it's polished. So what happens if I just take that and put it polished side down? Okay, now think about it. the friction on the surface is the same as it was before. Only one side of the fault has lower friction. It's this polished surface. So now what am I going to get? Am I going to get still smaller earthquakes, or am I going to get no earthquakes at all? So here we go. So we almost get creep, but we actually get even smaller earthquakes, and occasionally we get a reasonable earthquake. And that we've accomplished by just having one side of the fault have low friction. And we have a creeping section of the San Andreas Fault, and we have a creeping section of the East Anatolian Fault and the North Anatolian Fault too. And the San Andreas, we know that one side of the fault has very low friction. It's got clay materials. The other side is granite. So it's almost identical to the situation we have here. So think about it. We've gone from big earthquakes to no earthquakes or very, very little earthquakes. And the only thing that we changed is the friction on the fault and the mass being moved. Okay, now you might say, well, now, wait a minute. Earthquakes, you don't have an earthquake in isolation on a fault. So let's create a series. And so now I'm going to put 3 earthquakes in series, 3 faults in series. All right. And so now I want, again, you see what we've got. We've got 1, 2, 3. Who's going first? This guy or this guy? Well, who's going second? Who's going third? All right, so here we go. It's really interesting, really fast, right? We saw this guy go a few times before this guy went, and sometimes this guy went, but once they went all together. And this is another problem that we have in earthquake prediction, because no little earthquake knows it's marked for future greatness. Generally, it might behave on its own, stressing the next segment of the fault down the road. But at some point, if the rubber bands are taut between them, in other words, if everybody is ready to go, that little guy can bring along its sisters, and suddenly we have a big earthquake. And that happens. And in fact, it happened in the magnitude 7.8 in Turkey, and it's happened on other earthquakes, such as the Landers earthquake in 1992. So that ability of earthquakes of different sizes to occur on the same fault because of conditions that are very difficult for us to know is critical to the problem. Okay, now the last thing I want to show you is the most important, and that's called the Coulomb criteria for reactivity. So what I'm going to do for that, I'm going to take this guy here, and I'm going to get it. So it's about ready, don't go, about ready to go, all right? All right, now what I'm going to do is lift up the top brick, but I want you to tell me what's going to happen when I lift up the top brick. I get an earthquake, right? Because I've unclamped the fault. If you think about a subduction zone fault, it's kind of like this, but if you think about the East Anatolian fault or the San Andreas fault, it's like this. And so the bases of the fault have this enormous overload that pushes them together. If we can unclamp that just a little bit, and the fault's close to failure, we can trigger an earthquake. And by the same token, if I get it just about ready to go, and I pull on that rubber band just a little, again, I can trigger an earthquake. And what's important is, look at this. Now, there's not much load on this. That doesn't do anything. That doesn't do anything. So the Coulomb criteria only works if the fault is close to failure. And if it is, then an earthquake in the surrounding area, if that either unclamps this fault or pulls on the spring, we can trigger another earthquake. And that is our easy way into this ridiculously hard problem. We may not be able to predict that big earthquake, that magnitude 7.8 on the East Anatolian fault. But once it's occurred, it has changed the conditions for failure around it. It's pulled on some springs and loosened others. It's thrown on another brick or lifted a brick. We can calculate that. And that can tell us where the next large earthquake can occur and where aftershocks are going to occur. And that's what we can do with these limited tools we have, given this enormous range of variability in the Earth's machine. And as I leave this, I just want to say this is called QuakeCaster. That we have build instructions and whatnot for people to use it. Okay, so now I'm going to share my screen, and away we go with the slides. Okay, so what I want to do now is take you from the one-dimensional world where I am happiest to at least two dimensions, which is a little bit closer to what the Earth is like. So what we're going to do here is we're going to put the North Anatolian Fault on. We're going to put a square grid across it, fly overhead, and watch stress accumulate on the fault. So what's happening, I'm going to stop it for a second. There's this giant shear vise that the fault is caught in. And as these squares shear into parallelograms, that's equivalent to pulling on the rubber band. Okay, so watch them all start to shear into parallelograms, and eventually the stress overcomes the resistance on the fault, and the fault displaces. And now we can see that we've further sheared some of these blocks. So these guys out here are very, very strongly right laterally sheared, so they're colored red. These guys in here are gently left laterally sheared. They've been back sheared, so they're colored blue. So these zones are where we pulled on the spring, the rubber band, and here's where we've eased the rubber band. Okay, and so now let's think about clamping and unclamping. So where we've stretched our blocks, here, we basically pulled them apart. We've lifted a brick here and here. And here, where we've squished our squares, we've added a brick here and here. And the Coulomb criteria is simply multiplying this panel by the friction, about a half, and adding them together. And when we do so, we get the Coulomb criteria. And that is shown here. All right, so now we've added them together and we have the conditions for failure. So failure is promoted. You can see these little arrows down here. And so what's happened here is that these yellow and red areas are where faults parallel to the slip fault have been brought closer to failure. And the blue areas, which we call the stress shadows, is where they've been brought farther from failure. And so we now can see that beyond the ends of the fault, we have these kind of blowtorch zones where we would expect aftershocks to occur. But we also have these a little bit more subtle off-fault lobes where we would also expect earthquakes to occur. All right, so now let's take this to California, where these ideas first materialized. Okay, so here we are in Southern California, and this 1992 Landers earthquake is a perfect example, by the way, of three little wannabe faults that got together that couldn't have knocked off a magnitude 6.5 if they had tried, but they got together in 20 seconds and made a 7.3. It's the three bricks that suddenly moved together. And now you're a little bit more familiar with the pattern of stress calculated here. These are the aftershocks in the first 3 hours. And then what happened is after 3 hours and 8 minutes, we had a magnitude 6.5, about 30 or 40 kilometers off the main fault, on a different fault. And when you think about it, this is the Turkey situation. The biggest, it's just scaled down here. We had a 7.8, and several hours later, 9 hours later, we had a 7.5 on a different fault. So remarkable similarities. And the question is that 7.5 also occurring in a stressed zone? Now, you might look at this picture and say, oh, wait a minute, you know, he's making a lot of noise about this, but I could practically throw a dart at this map and hit some red or yellow. So prove to me that this is actually what controls seismicity. And I can, because we have 10,000 aftershocks. And the majority of those aftershocks are occurring in the yellow zones and are not occurring in the shadow zones, and including the magnitude 7.1 that occurred 7 years later, and a magnitude 7 that occurred almost 3 decades later. And that tells us that to some extent, static stress changes influence seismicity for periods of at least hours and probably minutes to decades, many decades. And so that's the strategy that we're going to try to use to understand what happened in Turkey. And by the way, we have software. This is called Coulomb 3.3. You can download it. It's on Temblor's website. Many people use it. It's a MATLAB program, and that's what it's for. Okay, so now let's take this to Turkey. And here is the first earthquake, the magnitude 7.8. And it's no surprise to now that you see what this pattern is. These are the blowtorch zones beyond the ends where we see a lot of aftershocks. And then we have these weaker zones as the side lobe. And what's interesting about this is that we had the 7.5 in one of these side lobes. And we can go and look at what happens after that 7.5 occurs. And you can see that the pattern has changed. The pattern of aftershocks has changed from what it was before. So originally we had aftershocks out here and here. And by the way, we had none here and none here. And now we have this kind of east-west band of aftershocks and aftershocks occurring farther to the southwest. So broadly speaking, we can see that there's a relationship here. Now, since the time these calculations were made, much more information has come in on the nature of the rupture. And so I want to show you that next. So this is work by Shoni Johnson at KAUST based on satellite radar interferometry. And you can see in much more detail the nature of the faulting and the amount of the slip. And seeing how much it slipped, let's say 5 or 6 meters over almost 300 kilometers for the magnitude 7.8, and 7 or 8 meters over about 100 kilometers for the magnitude 7.5, we can ask ourselves one crucial question. Is this earthquake improbable, or is it just rare? And here's the question that we need to ask, because many people said, oh, I never thought it possible that an earthquake this large could have occurred on this kind of secondary fault. Well, the fault has a 10 millimeter per year slip rate. And so if you think of 6 meters, then that would suggest a 600-year repeat time. But that's a gross underestimate because there are smaller earthquakes and they soak up some of the slip. And if there are larger earthquakes, and it's a 600-kilometer long fault, so it might even be able to host an 8.1 or 2, then those even rare big earthquakes soak up a lot of the slip. So this is probably not the right way to answer the question. But we have another way to answer it, which is Temblor has what's called a stochastic event set. It's 50,000 realizations of next year worldwide, 80 million earthquakes. And when we put a box around the East Anatolian Fault and say, okay, what's the repeat time for magnitude 7.8? We get about almost 1,800 years. And that's a not quite 2% probability in 30 years. So what's the answer to the question? It's rare, but it is not improbable. And thinking back on Quakecaster, you can see now there's always the possibility of yet larger earthquakes. And so we cannot eliminate that possibility. And if anything, even calling this a 600-kilometer fault is probably inappropriate because the fault makes kind of a left turn and becomes the Dead Sea fault zone. But these faults may not know that they have different names. Okay, with these better slip models, let's analyze the interaction in a more, perhaps deeper way. Still simple-minded, still elastic, but deeper way. So here is the two main shocks and the faults. And the first thing that strikes you about this is neither of these earthquakes struck on the East Anatolian Fault. So here we have this fault with a 10 millimeter per year slip rate, and these mangy little side guys are the places where these earthquakes occurred. And that is not good news for earthquake prediction because it means you have to monitor everything to find the fault that actually could launch this kind of episode. And there's something else of interest too, which is The 7.8 nucleates on this secondary strand and then jumps onto the East Anatolian Fault and then ruptures in both directions to the northeast and the southwest. And you go, boy, that's pretty strange. Why isn't it rupturing on the big fault? Well, we actually have two similar sized examples, very recent ones, that did the same thing. So this is not unique to this case. It's like a kind of a freeway entrance or a highway entrance where you get going and you get onto the main route. And recent work, just a couple of days old, from Razakis and his colleagues at Caltech suggests that first 20 kilometers, when this rupture got itself onto the East Anatolian Fault, it was rupturing at super shear speed, at much faster, about 50% faster than the shear wave velocity. And that creates kind of unique conditions that may have promoted its ability to jump. So it's a very fast freeway entrance from this little mangy side fault to the main one. But then you can also ask yourself the question, well, wait a minute, how common is it to have an aftershock, a 7.5 with a main shock of 7.8? Aren't people telling us that the largest aftershock is supposed to be a magnitude unit below the main shock? No, earthquakes don't follow our rules. And in fact, that kind of phenomena of several main shocks or very, very large aftershock is also not unique. You know, here's 4 examples. I showed you one with the landers in Big Bear a couple of slides ago. So this kind of phenomena of several large earthquakes is not unique. Okay, so now what do we want to do? We want to use the slip model for the magnitude 7.8 to calculate the stress that it transferred to the rest of the East Anatolian Fault. And so here that calculation is. So like you saw in the map view before, the areas where there was a lot of slip turns blue, and the surrounding areas, the blowtorch zones, turn red. And that's kind of what you would have expected. Okay, and as you saw, we saw aftershocks in this zone and in this zone. But what about where the 7.5 occurred? So let's now resolve the stresses on a simplified, idealized plane of the Surgu-Kardak fault. So here we go. And now we see something really interesting. That fault was brought closer to failure by the main earthquake by a significant amount. So even though it's a sideshow fault, it was stressed by the main one. And retrospectively, looking backwards, we can see that this played some role in why that 7.5 occurred where it did. But we're not really out of the woods yet because there's still some problems with this fault. The compression direction is roughly north-south. And you can see how if you start squeezing the East Anatolian Fault, it'll move left laterally, which simply means that the other side moves to the left. But that compression direction is almost perpendicular to the Surgu Fault. So how do we get it to move? And this isn't unique to this situation. We have a similar kind of fault in California called the Garlock Fault, which is also almost perpendicular to the compression axis. So think about it this way. You're eating a watermelon, in Turkish, a karpuzi, and you take one of those seeds out of your mouth and you put it on the table and you put your thumb down and you push and it goes bing. Because it's very slippery, it can fly. Now come back the next day with that same seed, put it on the table and push, it won't go anywhere. So what that tells us is even under these conditions that you have a misaligned fault relative to the compression direction, the only way to get it to go is if it's very slippery. I don't know what that is, fluids, material properties, whatever it is, these misaligned faults need to be very slippery to move. That's the only way you can get them to go. Okay, so what do we see here? We've added stress beyond the ends of the fault, and we've added stress to the Surgu fault. Okay. Now let's think about what happens when let's look at what happens when the 7.5 occurs. All right, so now on the right is the stress transferred from the magnitude 7.5 to the Surgu Fault and back to the East Anatolian Fault. And now, again, you can see in the area of high slip, it turns blue. It turns on the western part of the fault, and it adds to the stress that's occurring to the northeast here. And something of interest, which is that in this area, the area that slipped high, it's now fallen under a stress shadow. So the effect of the 7.5 is to turn on parts of the fault and to turn off other parts. So we're seeing stress toggling back and forth between these two earthquakes. Now, is that something that actually shows up in the aftershock process? And the answer is maybe. So let me show you what we get. So on the left, I've shown you the aftershocks in the first 9 hours, the aftershocks from the magnitude 7.8 to just before the 7.5 occurs. And on the right, I'm showing you from 9 to 90 hours. Now you're going, well, why are you doing that? Why aren't you just putting the same amount of time in each panel? And the answer is because aftershocks have a 1/time decay. And what that means is that in the first day, you get the same number of aftershocks as you do in the next 10 days, and as you do in the next 100 days, and as you do in the next 1,000 days. So their frequency decays with 1/time. Their magnitude doesn't decay at all. You have the same largest magnitude in the first day, typically, as the next 10 days, et cetera. So we would expect the same total number of aftershocks in both panels. All right, what do we see? So here we get 9 shocks in this blowtorch zone, and afterwards we get 18, where we've increased the stress from the effect of the 2 earthquakes. And here, where this guy is now shut down by a shadow, it goes from 6 shocks to 1. So both of those seem to be consistent with the idea that the effect of the second earthquake is to shut down the central slip zone of the first. So, but what's peculiar about this picture is I promised you that you get the same number of aftershocks in both panels, but I'm lying. There's many more aftershocks in the second panel. So something happens here that increases the aftershock activity. So let's look at the cumulative aftershocks with time. So on the left is the map that you've seen with the 2 ruptures and the aftershocks. And we can kind of explain these in terms of this area being shut down, this area turning on as a result of both earthquakes, this one turning around on because of the 7.5, and this one turning on because of the 7.8. And on the right is the cumulative number of earthquakes with time. And here's what a 1/T decay looks like in linear time and linear amount. If we used a log-log plot, it'd be a straight line. And so the interesting thing that you see is that Turkey is kind of weak compared to earthquakes of similar size. And even more interesting, if you, in the weird math of magnitudes, if you add a 7.8 and a 7.5, you get a 7.9. So the Turkey sequence should be very comparable to Wenchuan, China, and it isn't. It's got about half the earthquakes or so of Wenchuan, and even less than just a 7.8 on its own, the Kaikoura, New Zealand. So then is that weakness of the aftershocks a product of the stress shadow triggered by the 7.5? I don't think so, because when you look carefully, you see that even before the 7.5 occurred, the rate of aftershocks was much lower than its brethren. And in fact, it was raised when the 7.5 occurred. So the 7.5, this phenomena of the conjoined area of high stress seems to dominate over the effect of the shadow. But whatever the reason why its aftershock productivity is low, it's good news. Because if the probability, if the rate of small aftershocks is low, the probability of large damaging aftershocks is also relatively low. And as we all saw in these terrible videos of building collapses all of these occurred, all of these video collapses occurred in aftershocks. So aftershocks are extremely dangerous to already weakened buildings. So hopefully we won't have an enormously high rate. Okay, we've looked at how these earthquakes interact and how they're changing the aftershock process. Let's now look at why we had an earthquake in this part of the world on this fault in the first place. So here is what's the Anatolia region, and you can see that it's bounded by the North Anatolian Fault and the East Anatolian Fault. And I've also shown that portions of both of these faults creep, just as this portion of the San Andreas does, and just as I showed you in Quakecaster, is something that we can anticipate if we're able to bring the friction down very low in a certain area. They partially creep and they also produce large earthquakes. So what's going on here is that the Arabian plate is pushing its way north into Eurasia and squeezing the Anatolian plate out to the west. And as it squeezes out here, it spreads with all these stretch marks, which are normal faults, extensional faults. And it flows into the Aegean, and then it gets shoved under Crete in what's called subduction. So that's the broad picture of what's going on in this fault. And you can see that these earthquakes have more or less occupied about half of the total East Anatolian fault zone. How fast is the fault moving? If we look at a box like this, which more or less captures where these two earthquakes were, and look at the GPS displacements in those boxes, and just draw those displacement values, you can see you can fit it with a sigmoid. And the total offset of the red line from here to here is 10 millimeters per year. And the width over which this occurs tells us the depth at which the fault is locked, and it's about 15 or 16 kilometers. So what is a 10 millimeter fault? In California, it's the Hayward-Rogers Creek Fault or the Calaveras Fault. 10 millimeter per year faults are relatively rapid, but they're still nowhere near the North Anatolian Fault and the San Andreas, both at about 26 millimeters per year. So we have some sense of why the earthquake occurred, where it occurred, and how the two main shocks interacted and how that's controlling aftershocks. But the stunning disaster of this earthquake, of course, are its destructive power. And these proxy damage maps from space show that huge urban corridors have been wiped out as a result of this earthquake. So what I want to do now is stop sharing my slides for a minute and show you another demo. Okay, this is a building that you'll see everywhere on Earth. We build buildings out of stacked cubes. I don't know why. We seem to want to put people in closest packing configuration. The problem is that a cube has no structural integrity. If we want to be technical about it, a tetrahedron. And what that means is that this building depends for its safety on its corners. Now, what does an earthquake do? Principally, it moves the ground from side to side. And if these corners are weak, the building is going to deflect enormously. Earthquakes also produce torsion. And you can see again that this building is very, very weak in torsion. And if any one of these corners breaks, this building is coming down. And if you don't believe me that a cube has no structural integrity, look at this. IKEA house, put it in your SUV and drive it home. Okay, here's the exact same building, but now I've just snapped in, literally with sewing snaps, these little triangular corner braces. Nothing. Okay, tell me, how much more expensive is it to build this building than this building? What's your estimate? It's less than 5%. It's not a big number. And in a reinforced concrete building, which is the typical building style in Turkey and pretty much around the world, particularly for tall buildings, we obviously don't have these corner triangles. What happens is there's rebar, steel reinforcing rods inside the concrete columns and beams, and that splays outward in the corners and is wrapped and is strengthened more in the corner than anywhere else. But the problem is that as an occupant of the building, you don't know what's in there. And the world would be a safer place if concrete were translucent, because we don't know when we're in the building if it's been built properly or not. Share again. So let's look at what can be said about the performance of the buildings in this earthquake sequence. 12,000 collapses, another 25,000 that will be demolished. In contrast, 9 base isolated hospitals, and those are buildings that solve the problem by having rubber and lead gaskets at the base, are fully functional. So modern design works, but obviously there was a lot that didn't work. So what went wrong? What can we say? One of the important things that hasn't really been captured in the news is that in many cases near the fault, shaking amplitudes exceeded the code requirements. And I'm showing you that in these 2 figures below. So let's take a look at these. The thick blue line is the code requirement, the most stringent code requirement. That's this guy. And the other lines, the squiggly lines, are the actual recorded motions. And anything in yellow there exceeded the codes. And unless the builder put a great cushion between the code and the design, it means that this building was potentially damaged. Now, the other problem are low code compliance with the modern codes. After the Izmit 1999 earthquakes, the codes drastically were improved, but there's not insufficient compliance. And unfortunately, there's illegal activity between inspectors and builders that meant that many buildings were either below code or ultimately were admitted on the basis of a code amnesty. Now, how does this relate to buildings? So a building is basically like a child on a swing, except it's upside down. And when you push a child on a swing, you know that the longer the swing, the longer the time between each push. And you know that to make the child really go higher, you have to push when they're going down and forward. So in other words, if the input shaking or the input motion that you're providing to the child matches the resonant frequency or the fundamental frequency of that swing, the motion keeps growing. And for a 6 to 12-story Turkish building, that's about a half second to a second. So that's the danger zone. So it's in these gray areas where the shaking, if exceeded the code, really spelled trouble. Now, I want to say something else that's equally important, which is that in addition to these failures, there are also great achievements in Turkey. Turkey has a mandatory nationwide residential earthquake insurance program. I'm in California, we don't. So we have only about 15% of the people in California have earthquake insurance. Turkey has an excellent seismic and geodetic network and extensive fault mapping. And basically, I couldn't have given this talk had those not been there. You saw the geodesy, the monitoring, the seismic data, all of which is possible because of what they've done, and a leading earth science and engineering community. So there are achievements, even though there are failures. And this isn't just Turkey's problem. This is the world's problem. So let's ask ourselves the question, how do Turkey's buildings stack up worldwide? Now, that's a difficult question to answer, but it's one we must address. So here's Temblor's view of building fragility. And in this global map, blue is good and red is bad. And not surprisingly, the United States and Canada, Costa Rica and Chile look good. Northern Europe looks good. Japan looks good. But there's a lot of red on the map. And Turkey is below average. Let's zoom in on Europe. One of the things that one can see here is that even within one country, there are big differences. Milan looks very resilient. Naples looks poor. And if we go down to the damage zone of the earthquake, we can see that it is poor as well. But there's a lot of red on the map. It's not just in Turkey. And what is concerning is that, at least in our view, Istanbul appears worse. So what does this mean? It means this is the moment for requiem and resolve. To grieve for the dead and to resolve as an earth science and engineering community that we can do better, and that we will use this moment to strengthen the protections of people and buildings, not just in Turkey, but worldwide, because this could happen to so many of us, and at some level, it will happen to every earthquake-prone area of the world, unless we use our insights to go forward. And the Turkish government has everybody that they need in their scientific and engineering community to get the advice to do what's needed to do this better. So let us resolve at this moment to make ourselves safer by saying we will not accept this to happen again. Thank you.